right, so we're going to go over some of the homework that was requested. And the first problem from 10.1 was number 31, and they say to take the exercise from number 21 and use the function f of x that we get and use that series you found from exercise 21, and then we're going to integrate it. And here you go, I'll show you the right here. It says, use the series and the function f of x that is represented from the indicated exercise to find a power series for the integral from 0 to x of f of t dt. Okay, so that's what our mission is. So from exercise 21, we needed to find a power series for this. And what the function was, if you expand this, if you let n equal 0, you get 1. Plus, and if you let n equal 1, you get 2x. If you let n equal 2, you get 2x quantity squared. And then you get plus 2x quantity cubed. Plus dot 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 plus 2x to the n plus dot dot dot. And you would find out here that this is geometric and that r is equal to 2x because you're multiplying by 2x every time. And this would converge when the absolute value of 2x is less than 1. And that means that 2x has to lie between -1 and 1. And then our interval of convergence is going to be 1/2 to -1, or -1/2 to 1/2. Okay? And so what they want us to do is find a function. Well, for part number 21, we found the function. Then if r is 2x, we can add up an infinite series. If r is between -1 and 1. And in this case, between -1/2 and 1/2, r will be between -1 and 1. And so we can say that this series sums to a sub 1, which is 1, over 1 minus r, which is 2x in this case. So the f of x that we were looking for in exercise 21 is 1 over 1 minus 2x. All right, but now the 31 says, take this information that we found, and we are going to try to find the integral from 0 to x of f of t dt. All right, well, what is f of x? Well, f of x is this function right here, 1 over 1 minus 2x. And we're going to say that that's going to equal then the integral from 0 to x of the sum, because we're summing an infinite series from n equals 0 to infinity of, I'm going to rewrite this as 2 to the n, t to the n, because we're integrating this now as f of t. And then we're going to go dt. All right, and then what is constant here? Let's think about what's constant. Well, if I'm integrating with respect to t is certainly not constant, but 2 to the n is constant. So when I find the antiderivative of this 2 to the n is going to go along for the ride. So the antiderivative is going to be the sum from n equals 0 to infinity. Well, 2 to the n stays the same. And then how do we integrate t to the n? Well, we raise the power 1. Here we go. This is t to the n plus 1 divided by the power, which is n plus 1. And now we've integrated it, and we're going to go such that we're going from 0 to x, because that's what the integral states. All right? So let's plug in x, and we get the sum as n goes from 0 to infinity of 2 to the n, x to the n plus 1 over n plus 1. And then when I plug in 0 for t, because I integrated with respect to t, this expression here, 2 to the n, t to the n plus 1 over n plus 1 goes to 0. So I just put a 0 here. And then we can say the integral is then the sum from n equals 0 to infinity of 2 to the n, x to the n plus 1 over n plus 1. Okay? Now, so I'm suggesting to you that that's the series that represents the integral from 0 to x of f of t dt. So let's see if that makes any logical sense to everybody. Now, what do I mean by that? I mean, let's actually do the integration of the function that we're finding. So let's do the integral from 0 to, I'll do that over here, 0 to x of 1 over 1 minus 2t dt. All right, and when we do that, the antiderivative of 1 over 1 minus 2t dt, if I were to use u sub, turns out to be negative 1/2, because the derivative of the denominator is negative 2. Natural log of the absolute value of 1 minus 2t, such that we're going from 0 to x. So let's plug in x. And when we plug in x, we get negative 1/2 natural log of the absolute value of 1 minus 2x. Minus, and let's plug in 0. When I plug in 0 for t, I get the negative 1/2 natural log of 1, which is 0. And so we get negative 1/2 natural log of the absolute value of 1 minus 2x. So we're going to suggest that these two are equivalent. Now, let's see if we're right. I happen to have Desmos open, so I can graph y equals negative 1/2 times the natural log of the absolute value of 1 minus 2x. Oh, and the natural log likes to have parentheses, so I got to do that. Picky Desmos, but we'll take it. All right, so, and then you notice we have a discontinuity at 1/2, which we would expect because of the log function there. All right, we're going to say y equals the sum from n equals 0 to, you know how picky Desmos is, we're going to do 25 of, and we said, make this so we can see it. We said our sum was, I'm going to do a fraction bar here, 2 to the n times x to the, I put parentheses here, n plus 1 divided by n plus 1. And I'm going to open this up so we can see it better. If you notice, and if I put the vertical limitations on here, x equals negative 1 divided by 2, and x equals 1 divided by 2, and I'm going to make them both green. And dash. Green and dash. Okay, so you see that the interval of convergence is negative 1/2 to 1/2, as we indicated earlier. And that's pretty cool that that actually does work. And so what did we do? We took, it helps if I undo my mouse here. We took a series that we found for 1, or we had for 1 over 1 minus 2x, and we integrated the summation, power series representation for it, and got another power series that represents the antiderivative of the very function we found in exercise 21. And you'll see between the IOC here of negative 1/2 to 1/2, they match pretty darn well. All right, so that's number 31. Let's do number 33, because that was another question. All right, so exercise 33. Okay, so on this one, what I recommend us rewriting is, this is the sum from n equals 0 to infinity of, I'm going to make this negative 1 to the n, and then I'm going to change this to x minus 3 over 2 to the n. Okay, because I just want the alternating piece to be separate. Because believe it or not, this is going to tell me what r is here. Okay, and if that's r, then I know that this will converge when the absolute value of x minus 3 over 2 is less than 1. And that's going to be negative 1, x minus 3 over 2. So it's going to lie between negative 1 and 1. Multiply all three sides by 2, I get negative 2 less than x minus 3 less than 2, and then I add 3 to all three sides, and we get, this is going to be 5 over here, and this is going to be 1. And interestingly enough, the IOC, interval of convergence here, is going to be centered at 3, and we go out to 5 and 1, and my radius of convergence here is going to be 2 on either side, which is kind of interesting. All right, so we're going to expect to see something that converges between 1 and 5 now. So now we have to come up with a function that this represents. Well, what does that represent? Well, it's going to equal a sub 1. Well, what is a sub 1? Well, I have to let n equal 0. When I let n equal 0, I got negative 1 to the 0, which is 1. And then x minus 3 over 2 to the 0 is 1. So it's going to be 1 over 1 minus r, which is x minus 3 over 2, which is a double-decker fraction. And I'm going to multiply everything by 2 over 2 to make it nicer. And we get 2 over 2 minus x minus 3. And then I could simplify this a bit by distributing that negative. And that's going to be 2 over 5 minus x, because if I distribute this negative, we get negative x plus 3, and 2 plus 3 is 5. So there we go. So this is our function from exercise number 33. That's our f of x. All right, so what we're going to do is we're going to find a representation for the integral from 0 to x of f of t dt. But we're going to use the power series they gave us, and I'm going to maybe we'll just use this version here. It really doesn't matter which one you use, but the constant goes along for the ride. So I think I'm going to leave the constant out here. So we'll say that this is the sum from n equals 0 to infinity of negative 1/2 to the n, x minus 3 to the n. Oh, I'm sorry, it's not x, it's t, because we're integrating with respect to t minus 3 dt. All right, and then what's constant? Well, the 1/2 to the n. So that's going to go along for the ride. If I find the antiderivative of that, we're going to get the sum from n equals 0 to infinity of negative 1/2 to the n. And then what do I do when I'm integrating t minus 3 to the n? Well, the derivative of the inside here is 1 dt. So I can just use u sub without the u here and say that this is going to be t minus 3 to the n plus 1 over n plus 1, evaluated from 0 to x, because we're integrating from 0 to x here. And then we get the sum from n equals 0 to infinity of negative 1/2 to the n, x minus 3 to the n plus 1 divided by n plus 1, minus what happens when I plug in 0 for t. This is where things get a little bit more interesting, right? When you plug in 0 for t, we get 3. Okay, so that's going to be minus the sum from n equals 0 to infinity of negative 1/2 to the n, negative 3, to the n plus 1 over n plus 1. And when I'm raising these powers to a power, negative power to a power, I think they're going to cancel, but give me a second to think about it. Fascinating. Okay, so you see how the question is saying from 0 to x? Well, in exercise 23, our function here is centered where? Our function is centered at 3. So really, we should be integrating from 3 to x, because that's where our center is. This, as I'm working this doesn't make any sense. So I think the book is wrong. Here I am going to argue with the book, right? Oh, how dare I argue with the book? But what we've got to integrate from where our center is. It doesn't make sense to integrate it from anywhere else. So I'm going to erase this piece, because when you put a 3 in for t, you get 0, which makes a whole lot more sense. Because I'm looking at that with a 0 in there going, nope, that doesn't work. So I'm going to put a 0 here, because when you put in 3 for t, you get 0. This is much more apropos, I think. So we get negative 1/2 to the n times x minus 3. I'm sorry, I shouldn't have the parentheses so big. X minus 3 to the n plus 1 over n plus 1. All right, so I'm going to do the same thing here, where I'm going to integrate what function we had here. I wonder if I have enough space over here. I'm going to try. Here we go. The integral from 3 to x of 2 over 5 minus t dt. And that's going to be 2, negative 2, right? Because the derivative of 5 minus t is negative 1. So that's negative 2 natural log of the absolute value of 5 minus t, such that we go from 3 to x. Okay. So what happens when we do that? We get negative 2 natural log of the absolute value of 5 minus x minus, I did add this right? This is 2 minus, yeah, that's right. Okay. Minus 2, this is minus. The natural log helps if I write right. Natural log of the absolute value of 2. Fascinating. All right, so let's see what happens when we do it on Desmos. I'm going to deselect these and deselect this one. And we're going to say y equals 2 divided by 5 minus x. And let's just make sure that that's equal to the same thing as we started with. 1 divided by 1 minus parentheses x minus 3 parentheses divided by 2. Yeah, that's the same function. So I did my math right. I don't know what I'm worried about. All right, here we go. So y equals the sum from n equals 0 to, we'll say, 25 of my nth term, which was parentheses negative 1 divided by 2 raised to the n times, oops, not 8 times, parentheses x minus 3 parentheses raised to the parentheses n plus 1, parentheses, and then n plus 1 in the denominator. All right, so there's my function. Now, you notice that I'm a little bit off here. Oh, I know why. Because this is the I got to take the antiderivative, which I did, which is y equals negative 2 natural log of the absolute value of 5 minus x. And I have to have parentheses here again, or Desmos will be angry. Parentheses. Minus 2 natural log. parentheses, absolute value of t. Where's that red function coming from? That's my original, I don't want that one. Did I do 23? Let's see if I did 23. Fascinating. All right, well, we're going to have to go to the next one. And if a brainstorm hits me when we come back, well, because the interval notation works. Anyway, I'm going to keep going on to number 61, and then I'll come back to that in just a second. All right, number 61 is next. And number 61 states, I just love it. We're modeling humanity. That's what we do every day, is model humanity. All right, so it says let S be the series here that is represented by the sum from n equals 0 to infinity of t over t plus 1 to the n, where t is not equal to 0. And the question says, find the value to which S converges when t is equal to 1. All right, so part A is pretty simple because we're just going to let t equal 1. And when we do that, then the sum from n equals 0 to infinity is just 1 over 1/2 to the n. And this is a geometric series, and geometric series converge when our absolute value of r is less than 1. And in this case, r is 1/2. So we can say that the sum equals 1 over 1 minus r, which is 1 over 1 minus 1/2. And that's going to be equal 1 over 1/2, which is equal to 2. So this series does converge, and it converges to 2. All right, so part A was a piece of cake. Part B says determine all values for t for which S converges. So if r is equal to t over 1 plus t, we have to find out when the absolute value of r, which is t over 1 plus t, is less than 1. Wow, and that's fascinating because that's a rational function, right? If you think about it, a rational function that we learned how to do in pre-cal, whose horizontal asymptote is at 1. Here it is. It's got a vertical asymptote at -1. There it is. If I plug in 0, I get 1. If I plug in 0, no, I'm sorry. If I plug in 0, I get 0. What am I talking about? Yeah. All right. And so t over t minus 1, or t over t plus 1 would look like this, right? If we were doing the graph like we were used to doing in pre-cal. Boom. Right? But what happens is that I want the absolute value of this function. So what am I going to do? I'm going to say, okay, well, this part is certainly going to work. And then this part works because it's already positive. And so I have to take the negative part and make it positive. So there we go. It looks a little squirrely, but there's the graph of the this is the graph in the dark pencil of the absolute value of t over 1 plus t. Now I have to figure out when it's less than 1. Well, this is y equals 1, so right here is an important point to me. I need to find out when that is true, right? So is this behaving the opposite of itself, or is it behaving the same as itself? Well, right here, I didn't change anything on the original graph. Here, I made it the opposite. So I need to set negative t over 1 plus t equal to 1, because it's behaving the opposite of the absolute value is forcing it to be the opposite here. So then I'm going to cross multiply. Negative t equals 1 plus t. And then I'm going to add, this is negative 1, equals 2t. T equals negative 1/2. So when t is negative 1/2 to infinity, then the absolute value of t over 1 plus t will be less than 1, and this will converge. What will it converge to? Well, what we would do is say a sub 1 over 1 minus r, and we know what r is, and we would put r in that equation, but it didn't ask us for what that representation was. Okay, but let's go on to part C. I think this is the hardest part, but it was fun. Find all values that make the sum of s greater than 10. All right, well, what is the sum? The sum is a sub 1. Well, what happens when you let n equal 1 here, or n equals 0? You get 1. So a sub 1 is 1 over 1 minus r. But what is r? Well, r is this t over 1 plus t. So we go t over 1 plus t. And we want to know when that's greater than 10. All right, so I'm going to multiply this side by 1 plus t over 1 plus t to clear the fraction, and I get 1 plus t over 1 plus t minus t has to be less than 10, or greater than 10, I'm sorry. And what happens to the denominator here is really spectacular because those t's cancel, and I get 1 plus t has to be greater than 10, so t has to be greater than 9, and that's when the sum will be greater than 10. All right, so that's number 61. All right, moving right along. Number 64. 64 says, if I make this bigger, or smaller I should say, 64 says, use differentiation to find a series for f of x equals 2 over 1 minus x to the third. Okay. Well, what are the series that we know? Well, we know this one, 1 over 1 minus x. That's the one we know. And we know that that one is the sum from n equals 0 to infinity of x to the n, right? Because it's 1 plus x squared, right? And this looks like it could be some kind of derivative of this one. All right, so let's say I have 1 minus x to the negative 1 is my y. And y prime is going to be then 1 minus x to the negative 2 times the derivative of the inside, which is negative 1, right? So I put a negative out here, bring the power down, negative 1, which turns out to be 1 minus x to the minus 2. Y double prime then is going to be negative 2, 1 minus x to the negative 3 times the derivative of the inside, which is negative 1, which is 2, 1 minus x to the negative 3, which is equal to what we have over here. So what do I need to do? I need to take the derivative of this power series twice. So it's asking me for y double prime, basically. All right, so I'm going to say f of x is equal to the sum, or 2 times the sum. Oh, no, I don't even need 2 times. The sum from n equals 0 to infinity of x to the n. F prime of x is equal to the sum from n equals 0 to infinity of, what do we do when we take a derivative? Well, we go power down function or to power 1. There you go. That's easy enough, right? But I don't know if that works. We'll see. We'll check out these limits here for n in just a second. What is the second derivative here? Well, you just take the derivative again. And that's going to be n times n minus 1 to the x to the n minus 2. Okay? And if I were to expand x to the n, this right here, it's going to equal 1 plus x squared plus x cubed plus dot, 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 plus x to the n plus dot, 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 right? So if I were to take the derivative of that power series, 1 plus x squared plus x to the third plus x to the fourth plus dot, 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 plus x to the n plus dot, dot, dot. What do we get? This is y. Y prime would be, well, this goes to 0. Then I get 1 plus 2x plus 3x squared plus 4x cubed plus dot, 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 right? Which matches what we would expect here. But a sub 1 here is 1. But if I let n start at 0 here, then the n gets wiped out here. So I need to have the n start at 1. Then let's see what happens if I let n start at 1. I get a 1 in front here, and then I get x to the 1 minus 1, which is 0, which gives me the 1 here. And then if I do y double prime, which is the derivative of this one, we get 2 plus 6x plus 12x squared plus dot, dot, dot. All right. Now, if I let n equal 0 here, I get a 0. If I let n equal 1 here, I get a 0. But I need my first term to be a 2. So I think I'm going to let n equal 2, because if n is 2, then 2 minus 1 is 1, times 2 is 2, and then I get x to the 2 minus 2, which is 0. So that works. So when you differentiate, oftentimes you have to check the index of summation starting point to make sure that it works for your derivatives. Okay, and let's prove to you that that actually does equal what we need it to equal. My dirty laundry here, we'll get that worked out. All right, so we're going to say y equals 2 divided by 1 minus x. Close the parentheses, raised to the third. That's my function that I'm trying to find the power series for. And I'm suggesting it's y equals the sum from n equals 2, because we're going to start at n equals 2 to, I don't know, we'll do 25 terms again, of n times, parentheses, n minus 1, close parentheses, times x raised to the, parentheses, n minus 2. And there it is. See how it works? It works beautifully there. Very nice. Unlike number 33, which is still haunting and vexing me at the moment. All right, so then that's number 64. So moving right along, the other question that was asked was number 72. What I like about 72 is this is a previous AP question. And so we like it, previous AP questions. This is kind of a big deal. All right, 72. F of t, they're telling me, is 4 over 1 plus t squared. And g of x is equal to the integral from 0 to x of f of t dt. And they want to find the first 4 non-zero terms in the general term for the power series of f of t. Well, we know this power series, I'm going to call this g of x. We know this is 1 over 1 plus x, which is the alternating, which is 1 minus x plus x squared plus x cubed, minus x cubed. Minus x cubed plus x to the fourth plus dot, dot, dot. And we're going to go negative 1 to the n, x to the n plus dot, 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 right? That's the summation notation here, 0 to infinity of negative 1 to the n, x to the n. But this has got a t in it, so I'm going to rewrite this as, this is going to be 4 times g of t squared. So how would I rewrite that? I would say, well, this is 4 times, now I'm going to put a t squared where I see x. So that's 1 minus t squared plus t squared squared minus t squared cubed plus t squared to the fourth plus dot, 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 plus negative 1 to the n, t squared to the n plus dot, dot, dot. All right? Okay, and so this is going to be 4 times, let's simplify this a bit, 1 minus t squared plus t to the 4th minus t to the 6th plus t to the 8th plus plus negative 1 to the n t to the 2n plus . And then if we multiply the 4 in, we get 4 minus 4t squared plus 4t to the 4th minus 4t to the 6th plus 4t to the 8th plus negative 1, what's the plus here? Negative 1 to the n, 4t to the 2n plus . Okay, so this is going to be equal to f of t, right? Because we are trying to find f of t, which is a transformation of g, okay? Now, if I want to write it in summation notation, it would be n equals 0 to infinity of negative 1 to the n 4 t to the 2n. All right, now, the first question asked for the first 4 non-zero terms. Well, guess what? These are the first 4 non-zero terms. All right, and the nth term. And this is the nth term. All right, so that's part A. Whew, part A done. Part B says, find the first 4 non-zero terms in this general term for the power series for g of x. Well, g of x right here is the integral of this. Okay, so g of x is equal to the integral from 0 to x of f of t dt, which is equal to the integral from 0 to x of the sum from n equals 0 to infinity of negative 1 to the n 4t to the 2n dt. And when we integrate that, what happens is the negative 1 is constant and the 4 is constant. The only thing we're going to integrate is the t to the n, 2n, I'm sorry. So that's going to be the sum from n equals 0 to infinity of negative 1 to the n 4t to the 2n plus 1. We raise the power 1 and then divide by 2n plus 1, such that we go from 0 to x. All right, and then we are going to go and put an x in here, and we say, all right, that's the sum from n equals 0 to infinity of negative 1 to the n 4x to the 2n plus 1 over 2n plus 1. And what happens then when we plug in 0 for t? Well, that just wipes everything out, which is really nice. Okay, so, but we need so we have the nth term. So we're going to say the nth term is negative 1 to the n 4x to the 2n plus 1 over 2n plus 1. And then the first 4 terms would be, we let n equal 0. First 4 terms, we let n equal 0. And that's going to be a positive number. And then this is going to be 4 x. Because if I plug in 0 for n, I get x to the first over 1 plus well, it's going to be minus, right? Because when I raise n to the first, it's negative. And then I get 4 x to the, when I plug in 1 here, I get 2 plus 1 is 3, 4x cubed over 3 plus 4 x to the, if I let n equal, this is n equals 0, 1, 2, and then this is going to be to the 5th over 5 minus 4x to the, I'm following the pattern now, to the 7th. And so those will be the first 4 non-zero terms for the series centered at 0. All right, and so then it says find the interval of convergence. Okay, so for part C, we got to find the interval of convergence for part A. So I'm going to go back up here, and okay, what am I doing what am I multiplying by every single time? You know, so my r here is not 4t squared. It's just negative 4t squared. Because if I take 4 and I multiply by negative, I'm sorry, try again. It's negative t squared, because if I multiply 4 by negative t squared, I get the next term. If I take 4t squared, negative 4t squared, and multiply it by negative t squared, I get 4t squared. So this here is my r. Okay, and so this is part C. All right, this will converge when the absolute value of negative t squared is less than 1, which means t squared, absolute value t squared, has to be less than 1. And if I take the square root of both sides, I get absolute value of x, it has to be less than 1. So it has to lie between 1 and negative 1, which is really nice. Okay, so that's the IOC. I'm sorry that I put part C in the middle here, but I could at least look at my series up here. And then part D says the interval of convergence in the power series in part B is almost the same as the interval in part C, except it includes 2 more numbers. So what would they be? If I had to include 2 more numbers in this IOC, I think it would be negative 1 and 1. So part D is negative 1 and 1, because I would just close the interval and those would be my 2 numbers. All right? So I clearly need to think about number 33, and I will get back to you on that. So forgive me for that, and we will do a quick update on that later. Thanks. Bye.